the comparison test. So I hope we can finish comparison tests and maybe one more method. Or if not, then this will be for Thursday class. So comparison test is one of the, I think, also easy to use. So basically, comparison test is we are going to compare some series with other series that we are known for sure. So for example, if we take a look the series, let's say the geometric. This is we can also say this is also a geometric. We can rewrite as a r n minus 1, right? So this is geometric, right? This is geometric. And we know the geometric as long as the ratio is less than 1, then it could be, it will be converged, right? So we can say this will be converged. And then if we have, let's take the other series, something like this. This is something that perhaps if you see like in practice or in exercise or in exam, like something that like this one, it kind of similar with this. But it seems like we try to, if we try to maybe think this as a function, or if you try maybe taking some n, maybe you will not see any conclusion. But if you can compare this with this one, and we know that this will be converged, perhaps we can try something out. Since this is a fractions, and we can compare this, that this will be less than this one, right? So no matter how we could see that if we plus this series, if we plus this sequences, then this one, we know this was is converged, right? And in a term of the numeration, this is the largest one. So this cannot greater than that, right? So intuitively, we could see that this could also be a convergence series. So we know, okay, we know that since we know the geometric one, and we can compute the sum of that series, then we can write some sort of conclusions that the series somehow will be less than 1. This one from the geometric. Okay. So this series is really straightforward. We are comparing the unknown series with other series that we know. Okay, so basically we could just say that let's say we are having the series an and bn, and we need to make sure that the an and bn is a positive terms. It means that it's not alternating. And then if the bn is convergent while the an is less than b, like we did before, then we know that the an must be convergent. So an is probably the one that we are looking for. This is the unknown. And then this is the known one. Okay. And then similarly, but you need to be careful now. If B now is diverged, if B is diverged, and see the differences. now we have that A is greater than B. Okay. Then for sure, because B is diverged and A is greater than B, A must be diverged. Now the problem will be if this is diverged and A is less. For example, if A is less, now that's a problem. And we cannot make any conclusion. We need to make another method. We need to write another method. And usually, what we can take from the direct comparison test, usually, we can compare with the geometric series that we can find easily, and we can compare easily with the series that we are looking for, and we can compare with the a P series. The geo is this one, and the P series is the one that we have 1 over n with power of P, and we can set the P. It can be greater 1, it can be less greater 1. If we set to be converged, then this will be the one. This is the diverged one. So to begin with, some example here. I take the example from the textbook. So if you see, we have this series. Let's say we have that 5 over 2n squared plus 4n plus 3. It seems like if we are unable to compare, we don't know how to measure. So since the denominator is positive, it must be positive, right? It must be positive. Since it's also a quadratic, it's a polynomial. So we know for sure that as n larger, so denominator larger, and the whole thing becomes smaller, right? So you could see that, oh, I think we can do something, and then we could try to find some series that can be applicable. So the way we see this example here, let me show you here just for a moment. So look at this, okay? This is the one that makes the part of the fractions is, I think, the highest degree, right? It's the bigger one. So we could think that perhaps if we could take, or maybe just take the number 5 plus 4n plus 3. This should be less than 5 over 2n squared. And this is for sure, right? It's for sure. And then, since we know the series for 5 over 2n squared, we can write, and we can say that this is the P series, must be convergent, right? This must be convergent. Then this also convergent by comparison test, or complete its direct comparison test. So the idea is just to compare, okay? Just to compare. So I think in my experience, for the P series like this, either 1 over n squared or 1 over n, that is going to be the most cases that you can take, because 1 over n is for the divergent, 1 over n squared is for the convergent. Okay, and the example number 2 is exactly what I've just taught. So we have the ln k over k. Now we could see some. Let's say we use our intuition, so that maybe we need something that over k, maybe just one over k, and then just let's see how it goes for the ln. And you can check the ln. Take 1 is 0, take 2, 0.6 something. And then you can see that if we want to compare, we take some numbers for ln k over k, 1 over k. So for k greater 1, or maybe let me start from, if we check n equal 1, equal 2, equal 3, okay, maybe 1, 2, 3, we see that maybe it's not really that, it's not increasing, or we could see that for k greater equal 3, the ln k is greater than 1, right? If you see the number of the ln, if you check through your calculator, there after 3, the number is greater than 1, right? Which means that this will, for most of the part, this will greater, right? So you need to be careful. Sometimes there are some sequence or series that maybe maybe increase for a while, but then at some point it is increasing, and then most of the time will be increasing. Okay. So this is one of the case. We see that at 1 and then 2, maybe it's decreasing, still less than 1. I mean, still less than 1. But then, because we are concerned about this one, after 3 or from 3 to n getting larger, it is going to be 1 point something at least, right? This is going to be larger than 1. Then we can say that, okay, this is greater. Now we know the 1 over k. We could take the series, harmonic series. So since a harmonic series, this will be a divergent. Okay. So now this is divergent. So this must be divergent. and then also divergent by direct comparison test. So far, direct comparison works as long as you can make this all satisfied, all the requirements satisfied. Okay. Any questions so far? As long as you can know how to use this, it should be okay. It should be okay. And the second test is still in the comparison test. It's what we call the limit comparison test. Okay? That is, I think, more applicable for most comparison. The direct comparison, it has some flaw, some weakness. So if you imagine, so this is the limit comparison test. So if we, for example, if you want to test the if you want to test this, then if we try to start from the 1/2 with power of n and try to compare that with this, of course, if we could see this, this should be this, right? Should be greater, right? Should be greater. But we know that this is a geometric, this is convergent. But doing this is not getting anywhere, right? We don't have a good conclusion. So so we write here that the 1/2 with power of n convergent. Let me write here is the geometric series. I will write here direct comparison test is or cannot be applied. Okay. So when this happens, the other comparison method that we can try is taking this limit comparison test. So this actually could be true. So we are taking the an and bn as a ratio, as a fractions, that when we take the limit, it will have some constant c, positive c, okay? And it could be both converge or both diverge. It depends. And you will see how to use it later. So let's say A is the unknown unknown series. B is our known series. So if we choose B, that is going to be perhaps diverged, and we get that the C is positive number, then A is also diverged. If B converge and C is positive number, then A is diverged. Okay? That's how we think. So this works as so if the M and M are positive numbers, and then the M is going to be, or in between M, this M, small and capital, there is some number C. Okay. And we set the definition here, AN over BN is close to C for large N. There is the big N that so we change the C with the AN over BN because it's close to C. This is when N is larger, or in our case it's larger than this integer capital N, and then we could see that this will be in between these two. So if B and converge, then the sigma M BN converges. And also the similar thing with if it's diverged. Okay, so let me just write. It also works if this is diverged, then this is also diverged. Okay, before diverged, it should be the left one. Okay. So this part is actually the direct comparison test. This is the direct comparison test. So this is actually how they come up with this limit is basically they using the direct comparison test, and they are trying to make up some intervals, make up with some finite interval, and then they are using this A and BN to make up this nice interval, which if this is going to be true, then if the BN is converges, then this is also converges, and if this MBN diverges, then this M by N also diverges. And so the AN will converge or diverge depends on the BN. Okay. So if BN diverges, the AN will also diverge. If converge, then AN also converges. Okay. This is a small proving, easier to see and follow. Now, moving back to the original question that we start for the limit comparison test. So if we take this limit, okay, now we can rewrite perhaps as A, and then the other one as B. And then we can take the limit Okay, let me flip this. And then we can divide with the 1 over, let me write here to make it clear. I will multiply with this. So this is 1, 1. So the result is 1. Okay, this is 0. Which means this is a positive, right? You write a positive value. And since convergent, then also convergent by limit comparison test. And I think compared with the direct comparison, the limit comparison will work for anything that can be compared, that easily can be compared, and usually it will be mostly it will be a fraction. It will be a fraction. Okay, another example. If you look here, we can configure the fraction first. Then we can decide, okay, the one that is dominant or larger is this one, and the denominator will be this, right? So that is going to be our proposed series to be compared with this one. Okay, so first we can take an is that let's say 2n squared plus 3n and bn. I will take 2n squared, the dominant one, and this one will be n with power of 5 and a square root. So n will be power with 5 over 2. And we can solve this simplified. Minus 2 is half, so 2 with over n power with half. And then directly we can write limit I will simplify it. Or let me write n with power half. And then basically we are going to solve it like in limit evaluations. So 4/2 minus 1 is 3, right? 2 and 5/2. 1 plus 1/2 is 3. And then let's divide with the biggest n in our case, which is 5/2. So we divide all. Let me make a space here. So this will be 2 plus 5 with 1/n, 5/2. So 5/2 is minus 5. It's minus 2/2 minus 1. So 3/n, right? Okay. And then this one will be, this actually similar with this, right? Okay. And we know that this will be 0. This will be 0. And we have 2 by 2 is 1. So it's also a positive terms, which means that we can make a conclusions from the B. So since the Bn, the series is, or let me just write the series, 1/square root of n is divergent. Then the series, let me just write an, it's too long. Also convergent. By limit comparison test. Yes. Good. Yeah, why I write convergent? Okay. I also surprised. I thought I was writing divergent. Okay, but anyway, the limit comparison test, it will work for, I think, most of the series that can be compared with. The direct comparison test is more, you need to prove which one is greater, which one is less. Okay? But this one, it could work for, I think mostly in every fractions in series. I think this will work. And sometimes it works also for, if there is a trigonometric like sine or cosine, especially if they are absolute trigonometrics. And we know for sure it could be, we could compare that directly because the cosine and sine basically it starts from -1 to 1, so it's in between. But if that is in absolute value, if the trigonometric in absolute value, we can see that it will be in between 0 and 1. So we can compare with other P series or geometric series. Okay. Now to come up with some conclusions, let me just take some example, okay, so that you can follow how to predict or assume what should we take as an action. So let's look on this all this series. This is supposed to be work with the comparison, okay? Either with the direct comparison or limit comparison test. Okay. We'll start with something simple first, okay, and then we can increase. Let's say number 10. Okay, let's say number 10. Or yeah, let's say number 10. Let me zoom in first. And see all the series within the comparison, they are all in fractions. So most of the case, let's say your cube, it should be a fraction in fractions. Because I think it's also related to the proving on the limit comparison test when you prove that an over bn. So somehow in the process, you will see some canceling or maybe some simplification process in between when you use the fraction. So let's try number 10. Anyone would like to try? Number 10. Okay. Oh, you want? Oh. Why? Yeah. This is also study. Nothing wrong if you don't know. Because it's larger, right? Yes.
More than one, more than zero. Jadi terus yang ini kan
Version. So you can write this since that is version. Okay, I think this could be done by, you can take the direct or limit comparison also works. But basically, what we can compare with is with the compare with this. Okay. With 1 over n squared, right? I think this is correct. So this is a limit comparison test. I think this also works for direct comparison, and as long as we can prove that the inequality will correct. For example, if we try to compare this, compare with this, we know for sure this will always less, since the denominator, the cube, is really large compared with the squared, right? So we could see only for this that this will be less. Okay? This is just a linear, so not really that fast, right? It's not that fast as the cube. So we can also take the direct comparison, okay, and have the same conclusion. This will be convergent. Okay. Okay, let's take a break, but maybe for just wondering, maybe try 19 and 33. Okay, let's continue just a little bit. So let's see number 19. Let's see number 19. So you see that we have a fraction 4 with power of n plus 1 over 3 with power of n minus 2. And from this part, we could see that we have dominant number, which is this, right? So we could think for number 19, we could think compare with, let's say 4n plus 1 over 3 power of n, or we could write this as 4 with power of n, or 4 power of n divide 3 power of n, or we could write 4 over 3 with power of n. And we know that this will be a geometric series, right? So this is geometric, and since the ratio is greater than 1, this will be divergent, right? So this is a geometric divergent, right? So looking on the series, or maybe let me just compare the number. So 4, and we have 3 power of n minus 2, and we compare with the 4 n plus 1 3 power of n. And since we have the minus 2 on the denominator, of course the left one will be higher, right? Okay, but since this is divergent and this is greater than this will be divergent. Okay, so I think that's quite simple. So this also divergent, so by direct comparison test. So there will be at least 2 possibilities for your comparison. One is using the p series, like in the harmonic series, or the 1 over n with power of p. The other one is the geometric series. That is 2 possible, most cases, that will be your choices to compare with. So you can focus to compare all this series either with the 1 over n with power of p or with the geometric. Okay? And geometric, it depends on how it performs. Right? Sometimes it looks like this. If we can get this geometric, which you can see the ratio is greater than 1, which we know that it will be the divergent. Direct comparison test is much easier to solve as long as you can satisfy the inequality. Limit comparison test, of course it will also works, but it takes time to write in the limit, in the limit rate for the ratio the a and b. So it takes time. So you need to choose which way you are going to solve. But I think as long as you can prove the inequality, I think direct comparison test will be very simple, very short, nothing to nothing really complicated for this one. And basically all the problems, they are taking the pattern really similar. Like this one, you see the dominant is n, this one is n cubed. So we are having n over n cubed, which is 1 over n squared. The same thing with this. Dominant is 2 square root of n, so we can compare with 1 over square root of n. This is also the same, n squared and 4. So 1 over n squared. So you can see how the pattern is. So every time you see the fractions and you see the dominant degree or power, then you could think of maybe this could be works for comparison test. Okay, maybe one more, and this is, I think, a little bit quite complicated. The right one is quite complicated. Even it has the factorial, which is a little bit unusual in the comparison test. So for this special case, number 33, this could work as, let's say our an is, every time you see like the inside the parentheses 1 plus 1 over n, perhaps at later time it could be converted into some special property in the exponent. But let me just write this e power negative n, and then bn. I will choose bn as, so that it could be works with the limit comparison test. So I would choose bn as the e power of negative n. Okay. This is also ratio, right? Or geometric, right? Geometric. So we could see that this is actually, or maybe just write this. So it's multiplication of 1 over e, which is geometric. And then I can take the limit for the limit comparison test. And of course, we can cancel this. And then we are finally get the result directly. So this will be positive, right? And then the series E is convergent. Let me write by geometric series, by geo series. So let me just write an, also convergent. or to make sure that we are correct, let me just write here that the R is equal 1 over E, and this is less than 1. And sometimes, let me get up here. If you see number 37, we have a sine 1 over n. This, if you remember in the limit, we have some special property. When you have the limit and then you have sine n over n, we could make that property as 1, right? If there's 0 or if there's infinity, we could rewrite that special property. And we could use that similar property with 1 over n. So we could compare with 1 over n. So we take the limit. So this is what we are expected to do within the number 37. So we are going to have, I will just write some so I hope you understand how to write this. I will just write the important cases here. So this will be remember that limit in calculus 1 when we have 0, or let me write with x, sine x over x is equal 1. So since this is the infinity, and if you can rewrite this and you can prove that this is actually the same, and it will be equal to 1. And that this also works. So we can know that since the 1 over n divergent, this will be also divergent. So this one also divergent. Okay. The rest, I hope you can try. I hope you can try some other numbers. I would like to continue for another method, which I hope at least I can give some idea. And I think after that, there's still 2 more methods, and then after that we have overview, strategy to how to check convergences. Okay. Yes. This one? Oh yeah, because 1 over n is divergent. 1 over n harmonic series is divergent. Agree? Yeah, from there. Using limit comparison test. Equal 1, equal 1. This equal 1.
Our limit test, if its limit is positive, then it means that our Vn, which we found before comparing,
Yes.
Suitable.
Yes.
And if this suitable series divergent of number, then our series also
Yes.
divergent.
Yes. 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 True. Okay, please try these other numbers, and especially if you can see the pattern, and I think for most of the case for the comparison test, as long as you know the pattern, it should be okay. It should be okay. Okay, let me continue. So the next test is the alternating series, which we are going to see this quite a lot. And the obvious way we are going to know what is alternating series is by looking at this -1 with power of something. So this is a clue that, okay, this is going to be alternating, which it can be positive, positive, or negative, positive, negative. It depends on when it's starting as a positive or negative, okay. But we say that, okay, that is the alternating series. Okay, so let me give you the idea and the theorem first, and then you can see how that will work through some visuals and maybe some proving if we have time. So if you could see, since we start from B1, B2, B3, and then we see that it's going to be, okay, first is B1 minus B2 plus B3, and you see that we have this requirement. The next term should be less. The next term should be less. So B1 is going to, the value, so if we ignore the signs, so the value B1, B2 is going down, okay? Now imagine we start this block, okay, minus some B2, and then plus B3, which is lower than B2, okay, maybe plus, and then it's minus again, it's plus. So suppose that is going to take a long time to reach like a large number, because every value that is large here is going to be very, very small. So it will end up at one point. Okay. So if we could see the term here, okay. So we start from B1, okay, and then we move back again B2, and then adding B3, which is less than B2, the distance. Okay, you see the distance. The longest one is the B1, okay, and then we go back B2, and then plus B3, and then minus B4, B5, and then getting smaller and smaller and smaller. You will see that somehow it will reach some point in this S here. Okay? At least that is what we can see from the illustrations. So it means that somehow, that if this is alternating, somehow that will work. If we plus this alternating series, it will be a finite at the end of the day. It will be finite. And then another condition is that now the limit needs to be 0 for this to be satisfied. Okay? Okay, maybe let me give you some idea. And if we focus on this picture, we have the S, and then S1, S2, S3, okay, until we getting larger and larger. So this is our end points here. This is our starting point. So start here. This end here. Okay. Now suppose that we have the S2. So let's start. If we take the S1, this is going to be just B1. S2 will be B1 minus B2. S3 is going to be B1 minus B2 plus B3. S4. Okay. Suppose that we take the S2. which is going to be positive since b1 is greater than b2. So this is positive since and then if we take the S4, we could see the S4 is actually S2. We can write as S2 plus B3 minus B4. So plus B3 minus B4. Okay. And this will be we can write this is going to be greater than S2 because B3 is greater than B4. So still a positive, and then it's larger than the S2. And if we see the even number, only the even number, we could see that the S2n will be S2n minus 2. You could try S6 and then S8 and then S10. You will see that this is going to be true. This is B and 2n minus 1 minus B 2n. This should be greater than S 2n minus 2. So we could see 0, S2, S4, S2n. And we can also write the S, let me write here. We could also write the S2n as B1 minus B2 minus B3 minus B4 minus B5. So we could conjugate the terms, okay, the two terms in between B1 and the last terms. Okay, so this will be going on until B2n minus 2, 2n minus 1, and then this is perhaps the last terms. Okay. And every parenthesis, this is going to be positive terms because they are going to be decrease and decrease and decrease, right? So let me write, let me go here. So S2n will be less than B1 for all n. Okay. If you could see from the way we have here, then there will be always, this is positive terms, this is positive terms. Okay. Therefore, since this is always like decreasing, if you remember the sequence, okay, so sequence of, let's say, the even partial sums is increasing and bounded above. Okay. So it is convergent by monotonic sequence. And we can call this as a limit for the 2n, and we ended up with the S. The same thing is happening for the odd partial sums. We take limit. The odd will be as to n plus 1, the terms. And we can write this as a and this will be and since this is going to be 0, this will be equal to S. So both odd and and even, they will have the same conclusions, that is S. So the whole series will be convergent. So you will see that we have a quite different perspective now. Within a series, we can see its sequence and we can see the whole series. So if we can see the, for example, this one, this is the series for so this is going to be -1 over n. Okay. From n equal 1 to infinity. If we could only see the sequence only, then this will be the sequence, the an. So this will be the an. But if we could see the Sn, it will be a positive value. You'll see, notice that for the Sn, you will see that it is going to be, let me just take this. So start from here and then it goes here, goes like a zigzag. And then it's going to be maybe around here, which is around this part. So perhaps this is going to be around 0.8 or 0.7. That's the Sn. And you will see the limit. It goes from here. It goes zigzag, and then it's going to be 0. Which is this is going to be true for the requirements here, which it says that it should be decreasing and the limit should be 0. Limit of only the sequence. Okay, if we see just this example here, which we drew the graph, okay, we know that this will be less and less, decreasing. The second one is 1 over n. If you take the limit, is 0. Remember, 1 over n in our definition is a harmonic series, right? It's supposed to be divergent. But if, in terms of alternating, it will be convergent. Okay. So within these realms of the alternating series, there will be a functions that if we ignore the alternating signs, if we ignore that, maybe the functions or the series is divergent. But because it's alternating, it may be convergent. So sometimes we call that conditional convergent. Okay. So there will be a absolute convergent, conditional convergent. But maybe that is for later part. Okay. But anyway, there is only two requirements. Okay. You need to prove its decrease. The second thing is limit. Okay. Take limit, make sure it's 0. Okay. But it is only work for this alternating series. Remember in divergence test, if you take limit and if it's 0, it doesn't necessarily to be convergent, especially if that is not alternating. So for alternating, you need to make sure decreasing and its limit for the sequence should be 0. Okay. And how to know the alternating? This part. Okay. This is for sure. This will be alternating. Okay. And that is the only way we can have the alternating series. So again, some knowledge on limit would be very, very helpful. Okay. Okay, maybe questions? Any questions first? The next part of this will be the how to because there will be a conditions where the series without the alternating series, perhaps it will be diverged, but because of alternating series it is converged. So diverged becomes converged. So we call that as a conditional convergence. Okay. We are going to discuss about that on the next page. Okay. So we have let me just using these two definitions. Okay. So the first one is we call it absolutely convergent. That is when the series, we take the absolute value and we know that it will be convergent. Okay. It will be convergent. And the second one will be the conditionally convergent. That is if, okay, the AN converges, but when the absolute value is divergent. Okay. It's similar to the harmonic series that we have. Okay. So if we have the harmonic series, so if we have this, so if you take the absolute value for this harmonic, we have the divergent, right? So this is diverges, but this is convergent, converges by alternating series. So we call this condition conditional convergent. And I think I forgot to write the last thing. It's actually just a conclusion. So if the series is absolutely convergent, it is convergent. Okay, it is convergent. So additionally, instead of having just converge or diverge within the alternating series, another goal is to know whether it will be absolutely convergent, conditionally convergent, or divergent. So first, you can check using the alternating series theorem. So by alternating series theorem, there are only two requirements. The series should be decreased, and the limit is going to be 0. Okay, so first is, I think if you can see from this part, you can imagine, take the limit. I think at least this is going to be 0, so we can write here. So we can take the absolute value for each one of them. So we have and we know that this will be a convergent by P series, right? And then for B, this is also P series, but it will be diverge. So this will be diverges, but this series is converges by P series. P is less 1. It converges by alternating series. which you can prove that by taking the bn plus n is always decreasing, and the second is the limit. Limit, this is also 0. So we call this one here, the number b. This will be, we call this is conditionally convergent. Number C, we could take the limit. Let's say limit for that -1 and 2n plus 1 and I think this limit doesn't exist because of the alternating one. So you see that we have a 1/3, 2/5, 3/7, and so on. And this could be start from positive, negative, and then positive. And minus dot dot dot. You will see that it is not going to be, so it will alternately change from positive 0.5 and negative 0.5. And that is true because if we take the absolute value, the limit is 1/2, right? 0.5. And since it is alternating between negative because of the negative, it will be 0.5 or negative 0.5. So we could also think this, maybe let me just erase this one here. So we could also consider, since this is going to be 1/2, or maybe to make it clear, absolute value. So you see that this has a number here. So it's not 0. So the limit is not 0, it's 1/2. So by implication of this is the series will have jumped from 0.5 to negative 0.5. So we could say by divergence test, it is convergent. Oh, why I'm writing convergent, divergent? Okay, that's the main content for the alternating series. You just need to add some exercise that you can finish off next Thursday with I think the last method, the ratio and root test. But not for the chapter 11, we still have several subtopics. Remember, at the beginning of the chapter 11, our goal, we want to make sure that the series can be represented as a function, which later we see from the power series and the Taylor series. Okay. So that is actually our goal. So I think today's class, finished up until here. Maybe any questions before we end? And if you haven't checked your quiz, you can check. Or if you want to take for your friend. For quiz, you can take home. But for midterm, you need to give back to me. So for the midterm, for quiz, you can take. Okay, if there's no questions, so let me give you the attendance. Wait for a moment. Okay.